How do we know the exact time, down to a billionth of a second? The answer isn't gears or springs, it's atoms. For most of history, we tracked time with the sun, water clocks, and hourglasses, are useful but never precise. Mechanical pendulum clocks improved things, but temperature, gravity, even air pressure could throw off their swing. Quartz watches came next, a vibrating crystal instead of a swinging weight. Better, but still drifting seconds every month. But modern life needed something far more exact. GPS, the internet, even power grids, all needed perfect timing. The solution was hiding inside the smallest thing imaginable, the atom itself. Here's the key idea. Every atom of the same element is absolutely identical, anywhere in the universe. Inside an atom, electrons sit at fixed energy levels, like rungs on a ladder with nothing in between. An electron can jump from one level to another, but only by absorbing or releasing an exact amount of energy. That energy comes out as a photon, a tiny particle of light, at one exact unchanging frequency. This frequency isn't a guess or an average, it's a fixed constant of nature, identical every single time. Different elements tick at different frequencies. Hydrogen has its own beat, cesium has another. Scientists chose cesium 133 for atomic clocks. Its frequency is stable and practical to measure precisely. The specific jump used is called a hyperfine transition, a very small, very precise shift inside the atom. This natural vibration becomes the perfect metronome, one that never wears out, never drifts, never needs winding. So the plan became clear: build a clock that counts these atomic vibrations directly. Here's how an actual cesium atomic clock works, step by step, starting with the atoms themselves. First, cesium metal is heated in an oven until it turns into a vapor of loose atoms. Those atoms are released as a thin beam, traveling through a vacuum chamber to keep them undisturbed. A magnetic filter sorts the atoms, letting through only those in the right starting energy state. The filtered atoms then enter a microwave cavity, a chamber bathed in a tunable microwave signal. The microwave frequency is carefully tuned, searching for the exact number that resonates with the cesium atoms. When the frequency is exactly right, the microwaves flip the atoms into a new energy state. A detector on the other side counts exactly how many atoms made that jump. A feedback system uses that count to nudge the microwave frequency higher or lower, searching for the peak. Eventually, the signal locks on, the point where the maximum number of atoms flip states every time. That resonance point happens at exactly 9,192,631,770 vibrations per second, a number etched into the definition of time itself. In 1967, this exact number officially replaced Earth's rotation as the definition of 1 second. Before that, a second was based on how fast the Earth spins, but even the Earth's rotation isn't perfectly steady. Once locked to the atom, the clock counts these vibrations continuously. 9,192,631,770 counts equal 1 second every time. The result is extraordinary, accurate to within 1 second every 100 million years. But scientists pushed further, building optical clocks, using visible light instead of microwaves. Optical clocks use atoms like strontium or ytterbium, which vibrate far faster than cesium. Higher frequency means finer ticks and dramatically more precision packed into every single second. The best optical clocks are accurate to 1 second over the entire age of the universe. Today, atomic clocks also come in miniature form, small enough to fit inside a satellite. Let's recap the whole process. Heat the atoms, tune the microwaves, lock onto resonance and count. That precise invisible tick is now quietly running underneath so much of modern life. So where does all this precision actually get used? More places than you'd think. GPS satellites each carry an atomic clock because your location is calculated from how long a signal takes to reach you. Radio waves travel at light speed, so even a billionth of a second timing error can shift your position by meters. Telecom networks use atomic time too, keeping millions of calls and data packets perfectly synchronized. Financial markets rely on atomic clock timestamps. Trades are logged down to microseconds for fairness and accuracy. Power grids use synchronized atomic timing to balance electricity flow and prevent blackouts across regions. Scientists even use atomic clocks to test the fundamental laws of physics, watching for any tiny drift in nature's constants. Spacecraft exploring deep space are tracked using atomic clock timing, pinpointing their exact position billions of kilometers away. Even the internet depends on it. Servers around the world sync their clocks to atomic time standards every day. In fact, the global time standard we all use, UTC, is itself built directly from atomic clocks. Occasionally, a leap second is added to keep atomic time gently aligned with the Earth's slowly changing spin. Here's something even stranger. The atomic clocks aboard GPS satellites don't just measure time, they run at a slightly different rate. Being farther from Earth's gravity and moving at high speed actually changes how fast time passes for that clock. That's not a flaw, it's Einstein's relativity in action. And it's a story big enough for its own video. For now, what matters is this. An invisible atomic tick, discovered by studying the smallest particles, now runs the modern world. From ancient sundials to atoms vibrating billions of times a second, humanity's pursuit of exact time never stopped. So next time your phone finds your exact location in seconds, remember, it's an atom, ticking perfectly, making that possible. 1 second. Defined by 9,192,631,770 vibrations of a single atom. That's the quiet precision running underneath everything. And that brings us back to where we started. Now you know exactly how we tell time this precisely. If this kind of hidden science fascinates you, there's a lot more where this came from. Subscribe to Tech Beyond Earth. New explainers on tech, science and space are coming regularly.